Okay, in this YouTube I'm just going to work an example of a differentiator circuit because I didn't work it in the last YouTube. I think I was getting tired of making videos and I stopped. But okay, so you probably get tired of listening to me, so it's a good thing I break it up into another YouTube anyhow. So let's do that. Pick my pen here. So, okay, so I didn't really derive it last time, but let's derive it. So following our rules of op amps, the voltage here is the same as the voltage here. This happens to be at 0, so we know this voltage at A happens to be 0 also. And current going in here is 0, current going into that node is 0, so we apply Kirchhoff's current law to the node, and we have current going in, we have current must equal current going out, which is across the R. So I going into the node, which is IC, must be equal to I going out of the node, which is IR. So we do know that I in a capacitor is C dVc dt. And the I in the, so keep in mind that the voltage that's across C right here is the voltage Vn minus Va, and Va is 0. I could actually explicitly write that dVn minus Va over dt equals, and I is going to be, I in the R is going to be Va minus V out, Va minus V out over R. And so we know that Va equals 0. So then we get C dV in dt equals minus V out over R. And then we rearrange the terms and we get V out equals minus R times C times dV in dt. Okay, so that's our defining equation for this differentiator circuit. Now we need to plug in the values for this particular Vn that's given to us. Your textbook has a mistake in it. It says Vn is defined by these equations and is drawn in this figure down here, but then the figure says V out. So if you are on that figure in your textbook, I think it's page 236, this is really V in right here, and it is in volts. It's not V as a function of V, it's V as a function of T, and the units are in volts, and time is milliseconds on the horizontal axis. So this is our V in voltage. This is the equation that tells us what V out is. It's sort of convenient to calculate R times C. Keep your resistance, keep your units pure, keep it in pure ohms, pure farads, and you get R is 5,000 ohms times C is 0.2 microfarads, which is 0.2 times 10 to the minus 6 farads. And then you'll get a value of R times C, which is 10 to the minus third. And it turns out that R times C, farads times ohms, will give you, if you break it down into fundamental SI units, that will turn out to be units of seconds. I should show you that just to prove it to you, but R times C will end up with units of seconds. This will be important later on because we'll call this R times C factor a time constant. Actually, in the very next chapter we will start doing that. So then it's really just a matter of plugging in our differential equation right here. V out equals R times C times dV dt. Here is V in right here. We have to take the derivative with respect to time, and those are nice linear equations, so it's pretty easy. V out as a function of time will equal derivative of this. Derivative of 2000 t with respect to t is simply 2000, and that's valid between 0 is less than t less than 2 milliseconds. And then derivative of this with respect to t is minus 2,000 from 2 to t to 4 milliseconds. And this just repeats between 4 and 6 and 6 to 8. You don't actually have to do it again and again, but if you do, you'll just have this constant, like the next part will have a constant here for where the y-intercept is changing. So then it's just a matter of plotting that. If you plot that, it'll end up being on a different scale here. For the first time block, integrating or differentiating a constant slope is a constant. Then differentiating a constant negative slope will be a negative value. So this is 2,000 and this is minus 2,000. This is time here. Volts. Millivolts. Maybe it's millivolts. Nope, it's volts. Oh, two. Oh, yes, we do have a little funny thing here. So, yeah. And you all probably already caught it. I dropped off my R times C right here. There it is. I forgot to multiply everything times minus R times C in the front. So this is actually not correct. Let me just erase all that. That's actually not correct. My mistake. So if I multiply it times minus R times C in the beginning as the to satisfy this equation, then the equation, finally the equation for V out actually becomes V out equals minus 2 volts for the first time block and plus 2 volts for the second time block. And it repeats. So you do indeed, now it looks right to me, you get something like this for time. So when you differentiate positive slope, multiply it times a negative time constant in front, you'll have negative 2 volts. Negative slope part, differentiate it, you'll have positive 2 volts right here. And it repeats itself. So that's an example of a differentiator, and this time I went through and derived it like I should have done the first time. So I hope that that is helpful for you. It would be fun and enlightening to also do this circuit in Multisim. It turns out that this RC time constant plays a very important role in what this output looks like. Right now you see it as a nice square wave, but it could, depending on the value of R times C, be something not as a nice square wave. And we will show you that here very soon, I'm sure.